Hi, in this video, we are going to look at roots of unity, basically the complex roots of unity and some of their properties. So we define this root of unity as epsilon, which is cos of 2 pi by n I cap, cos of 2 pi by n plus I sine of 2 pi by n. Basically, this is my primitive root of the equation x power n minus 1 is equal to 0. So what we can say is this complex number definitely satisfies this equation, because when you raise it to the power n, you will realize that this will become cos 2 pi plus I sine 2 pi by De Moivre's theorem, and that is equal to 1. So that clearly satisfies this equation, right? So the equation x power n is equal to 1 has n complex roots, and these roots can be given by epsilon, epsilon square, epsilon cube, and so on till epsilon power n, which is actually equal to 1, right? So technically, the roots can also be written as 1 epsilon, epsilon square till epsilon power n minus 1. So these are the n complex roots of 1, and these roots on the complex plane will be the vertices of a n-sided polygon inscribed in the unit circle. Why is it a unit circle? Because x power n is equal to 1 implies that all the complex numbers that satisfy it must have modulus of 1. So they must lie on a unit circle of radius 1 in the complex plane, right? So these are the roots and they satisfy this equation. And the basic root is cos 2 pi by n plus I sine 2 pi by n, or e power I 2 pi by n. And any further roots are just powers of this primitive root. Let's look at some of the properties of these roots of unity. The first one is let k and l be integers, then epsilon power k will be equal to epsilon power l if and only if k is congruent to l mod n. Here we are saying epsilon was one of the roots e power I 2 pi by n of the equation x power n equal to 1, right? And we are saying that two different powers of the basic root will be equal if and only if k and l are congruent to each other modulo n. Okay. The second property is the product of any two nth roots of unity is also an nth root of unity, is also an nth root of unity. So that is an obvious property. Whenever you multiply, it keeps becoming another power of epsilon, and that eventually is an nth root of unity, because there is a cyclicity to this congruence. This is all congruent modulo n, and it keeps going in cycles, even if the powers are higher than n, right? The third property is this: let k be an integer and k and n have GCD equal to 1, or k is coprime with n, then epsilon power kl whole power l, where l is going from 1 to n, exactly gives all the nth roots of 1. So basically what we are saying is, because k and n are coprime, the numbers k, 2k, 3k till nk will form a complete system of residues modulo n. So therefore, they will give all the roots of all the nth roots of 1. So let's take an example to try and understand this property. So we are saying let n be the n be 3. We are talking about the cube roots of unity. The roots are 1 omega omega square. These are the cube roots of unity. And let's take a number k, an integer which is co-prime with 3, right? So we can take k as 5. We can take k as 5, right? That is an integer that is co-prime with 3. K and n is 1, right? Now the claim of the property was saying that epsilon, and this can be written as epsilon, epsilon square, and epsilon cube, right? Epsilon cube is basically 1 because epsilon in this case is cos 2 pi by 3 plus I sine 2 pi by 3, right? So what we are claiming is that epsilon power kl, which is 5l whole power l, right? Where L goes from 1, 2, and 3, forms the complete set of roots, right? So basically the roots will be what? Epsilon power, when L is 1, it will be 5. And when L is 2, it will be 5 into 2, 10 into 2, 20. And when L is 3, it will be 5 into 3, 15 into 3, 45, right? So now this is clearly going to be equal to congruent to epsilon square, and this is congruent to epsilon cube, and this should have been congruent to epsilon power 1, right? I feel like I have made some mistake there. Uh, so I think I have wrote the property incorrectly. What I mean to say is epsilon power k power L gives all the nth roots. It is not epsilon power kl power L. That's incorrect, obviously, right? So what is the property? Let me just rephrase the property. Let k be an integer such that k and n are co-prime, then epsilon power k power L gives, where L goes from 1, 2, 3 till n, gives all the nth roots of 1. That is the claim, right? So now let's see. We had taken the roots were e square, and e3, where n is 3, and we had taken L as 5, which is co-prime with 3. So what I'm claiming is e power 5 power 1, e power 5 power 2, and e power 5 power 3 are the three possible roots. So this is what? This is same as e square because e power 3 is equal to 1. E square, this is e power 10, so this is e power 1, and this is same as e power 3 to the power 5. E power 15 is basically e power 0, right? Or e power 3, whatever you want to call it. So we are getting all the roots, right? So the point is that it forms a complete residue system once you take e power k and raise it to the power L, where L goes from 1 to n, right? So that is the idea here. So what we can say is that epsilon is equal to e power I 2 pi by n is the most basic nth root, is the most basic nth root of unity, and because its integer powers, its integer powers give all the other n roots, give all the other nth roots of unity, we call epsilon as a primitive root, primitive root. And now we can say that for k and n being co-prime to each other, and 1 is less than k is less than equal to n, epsilon power k is also a primitive root, is also a primitive nth root. Why? Because powers of epsilon power k going over L, where L goes from 1 to n, give all the nth roots. Give all the nth roots, right? So, because of that, it is also a primitive nth root. So the total number of primitive nth roots of 1, primitive nth roots of 1 will be all numbers that are co-prime to n, right? Any number less than n which is co-prime to n, which is basically Euler's totient function. These are the number of primitive roots that you will find, right? Okay. Now we go on to some other standard properties. Because we know that epsilon, epsilon square, 1 till epsilon n minus 1 are the n different roots of x power n minus 1, we can write x power n minus 1 as a factors, product of factors of these. So we can write it as x minus 1, x minus e, x minus epsilon square, and so on till x minus epsilon power n minus 1, which can also be rewritten as x minus epsilon, x minus epsilon square, so on till x minus epsilon power n minus 1 multiplied by x minus epsilon power n. Here we have replaced this factor, we have called 1 as epsilon power n, which is correct. So these are two different versions of the same thing. And obviously, now we can divide, we know that x power n minus 1 can be written as x minus 1, 1 plus x square till x power n minus 1. This is a standard factorization. So combining first and third, we can deduce that 1 plus x square till power x power n minus 1 must be equal to x minus epsilon square till x minus epsilon power n minus 1. This is a standard result which you should be aware of. Now we can do a slight transformation here and get a similar result, but that is also the new result, which is also very useful. So what you can say is we have this 1 plus x square till x power n minus 1 is equal to x minus epsilon square till x minus epsilon power n minus 1. Now do the substitution x with 1 by x. So what will happen? You will get 1 plus 1 by x plus 1 by x square till 1 by x power n minus 1. And here you will get 1 by x minus epsilon, 1 by x minus epsilon square till 1 by x minus epsilon power n minus 1. Now at this stage, multiply both sides by x power n minus 1. So eventually what will you get here? X power n minus 1 plus x power n minus 2 till 1, which is the same thing as the initial thing here. But when you multiply x power n minus 1 here, split it into x different terms. You multiply x everywhere, right? That will be x power n minus 1 in total. You will get 1 minus x epsilon, 1 minus x epsilon square, and so on till 1 minus x epsilon power n minus 1. So this becomes your new identity, which is not something that was obvious immediately. So you have two different versions. This identity is true, which is obvious, but this identity is also true. You should keep this in mind. It will be handy in problem solving, right? The other properties are pretty standard. There is the property that sum of all the n complex roots will be adding up to 0. That is obvious from Vieta's relation in this equation. Sum of the roots in this equation must be 0. So that is an obvious property. Another property that is pretty commonly understood and known is this one. Let K be an integer, then 1 by n summation t goes from 1 to n epsilon power kt is equal to 1 if n divides k and is equal to 0 if n does not divide k. It's a very straightforward proof, so I will leave that to yourself. This is pretty easy. You can use the GP formula here to do it. Use GP formula on it, on LHS. So that is the hint. Now, one final statement that I would like to make here is for we know that e power epsilon power n is 1, and we also know that 1 plus epsilon square till epsilon power n minus 1 is 0. So from that, you can see that for any polynomial f of x, f of e, f of epsilon is either 0 or can be expressed as a polynomial in epsilon whose degree is less than equal to n minus 2. What does this mean? If you have a polynomial f of x whose degree was n and you have epsilon power n is 1, then obviously when you replace x with e, you will get terms like an epsilon power n plus an minus 1 epsilon power n minus 1 and so on, an minus 2 epsilon power n minus 2 till a1 x plus a naught, a1 epsilon plus a naught, right? So what we are saying is this term becomes a constant because epsilon power n is 1, and this term can also be removed by using this identity, and eventually you can replace epsilon inverse. Basically you can do epsilon n minus 1 is minus 1 minus epsilon squared till minus epsilon n minus 2, right? And if you replace that there, you will eventually end up with a degree n minus 2 polynomial in epsilon, right? So if f of x has a degree n, f of epsilon will be either 0 completely, or it can be a degree n minus 2 polynomial in epsilon, right? We will see how we'll apply this in a particular problem soon. So now these are the standard properties of roots of unity. I will look at a couple of questions. This is example 1. Let P of x, Q of x, R of x, S of x be polynomials, and it is given that P of x power 5 plus x times Q of x power 5 plus x square R of x power 5 is equal to x power 4 plus x cube plus x square plus x plus 1 times S of x. We have to prove that x minus 1 is a common factor of P of x, Q of x, R of x, and S of x. That is the question. Obviously, x minus 1 is a common factor means if we can show that P of 1, Q of 1, R of 1, and S of 1 is 0, then we know that x minus 1 is a factor for all of them, right? So here we'll do a nice solution, creative solution. Let epsilon be the fifth root of 1. Take it as the fifth root of 1, right? So we can say x can be equal to epsilon square, epsilon cube, epsilon power 4, right? We can take x as each of these things, and we can put x is equal to basically e epsilon power k in the equation. in this equation. Here k goes from 1, 2, 3, 4. Let's see what comes there then. We have p of x power 5, that is e power 5k, and we know that e power 5 is 1, right? So that is simply p of 1, plus we have epsilon power k q of 1, plus we have epsilon power x is epsilon power k, so it's epsilon power 2k, and r of 1, right, is equal to, on this side, we will get 0, correct? Because 1 plus epsilon power k plus epsilon power 2k plus epsilon power 3k plus epsilon power 4k is basically the sum of all the roots, right? Why are we getting 0 here? Think about it. This is 1 plus epsilon power k plus epsilon power 2k plus epsilon power 3k plus epsilon power 4k. So this is a property that we are taking 5 different multiples of e power k, right? If you take 5 different multiples of e power k and e was a fifth root of 1, you are definitely going to get all the possible residues. So this is a complete system, and therefore complete system of residues. So therefore this must be equal to 0. This will be basically all the different possible roots. So you are getting this equation, right? On putting x is equal to epsilon power k, we are getting this equation. And you can notice here that this is like x square p of r of 1 plus x q of 1 plus p of 1 equal to 0. This is a quadratic in x, which is equal to epsilon power k, right? This is a quadratic in x, but the nice thing about it is that this quadratic has actually got 4 different roots. What are the 4 different roots? Epsilon power 1, epsilon power 2, because k could be 1, 2, 3, 4, right? So x could be e power 1, e power 2, e power 3, e power 4, right? All of those will satisfy this quadratic. So that means if there are 4 roots of a quadratic, what happens? It is identically equal to 0, right? So that means immediately we are getting that P of 1 is equal to Q of 1 is equal to R of 1 is equal to 0. And if these are 0, it must be true. When you put x is equal to 1 in this equation, it is obvious that P of 1, Q of 1, R of 1 is 0. So S of 1 is also 0. So basically, it's a simple proof. If you take epsilon as the fifth root of unity and put it back in the equation, you will realize that you can make it look like a quadratic in x, where x is equal to epsilon per k. And that quadratic ends up having four different roots. So that quadratic is identically 0, which implies that p, q, r are all 0 at the value x is equal to 1, which in turn implies that s of 1 is also 0, and therefore P of 1, Q of 1, R of 1, S of 1 are all 0. So x minus 1 must be a common factor for all of them, right? You can work out the details yourself. The idea is pretty clear. Let's look at another problem. Prove that there doesn't exist, there doesn't exist 4 integer coefficient polynomials, 4 integer coefficient polynomials f of k of x, where k goes from 1, 2, 3, 4, such that the identity 9x plus 4 is equal to f of 1 x whole cube plus f of 2x whole cube plus f of 3x whole cube plus f of 4x whole cube is true. We have to show that there are not there cannot exist four different integer coefficient polynomials which satisfy this identity that the sum of their cubes is equal to 9x plus 4. Now, this is a tricky problem because you don't know immediately what approach you are supposed to take here. So what we will do here is let omega be a cube root of 1, cube root of 1. Now, since it is a cube root of 1 and we can write for any integer coefficient polynomial f of x, for any integer coefficient polynomial f of x, we can say f of omega should be a linear polynomial, right? Linear polynomial in omega, correct? Why linear in omega? Because omega means it is a third root of 1, right? So f of omega will always be n minus 2 root. If epsilon was a nth root of 1, we saw a property earlier that f of epsilon will be n minus 2 degree polynomial in epsilon, right? So here epsilon is equal to omega is basically a third root of 1, right? If it is a third root of 1, we can say that f of omega is a first degree polynomial in omega using that property that we saw earlier, right? So what will happen, we can write f of omega as a plus b omega, where a and b belong to integers because it's a first degree polynomial in omega, right? So then we can say f of omega whole cube will be equal to a cube plus b cube plus 3ab omega a plus b omega. We can simplify this by writing it as a cube plus b cube minus 3ab square plus 3ab square plus 3ab omega a plus b omega, and simplify this further as a cube plus b cube minus 3ab square, and we can combine this plus 3ab square with 3ab square omega square, and we have one term left, 3a square b omega. So this term will become 3ab square common 1 plus omega square, which is minus omega. And now I can take common between these two. So I'll be able to rewrite this as a cube plus b cube minus 3ab square plus 3ab, and this is a minus b into omega, right? So our f of omega whole cube is coming out to be a cube plus b cube minus 3ab square plus 3ab a minus b omega, right? Now notice that this coefficient, the coefficient of omega here is always even, right? This is always even because if you take a and b as both odd, a minus b is still even. And if one of them is even, anyway, product of ab will be even, right? So if this number is always even, similarly, we can say f of omega, we could have written f1 omega whole cube plus f2 omega whole cube in the same fashion. And you could always write it as sum of this plus some even number omega, right? So eventually we will get something like a plus capital B omega on the RHS, where B is even, right? However, the LHS was what? LHS was 9 omega plus 4. Because the LHS was 9x plus 4, here we are replacing x with omega. So LHS is 9 omega plus 4. RHS is a plus b capital omega, where b must be even because we have this as even. And you have four terms like this, right? So we are getting a contradiction because we are getting b should be equal to 9, but we are getting a parity mismatch. Even and odd is happening, right? So there is a contradiction, which means that it is not possible to select four different polynomials such that the sum of their cubes is equal to 9x plus 4. Notice that the last property that we saw, the property was for any polynomial f of x, f of e or f of epsilon is either 0 or can be expressed as a polynomial in epsilon whose degree is less than or equal to n minus 2. It is that property that we are using here to solve this problem. The other approaches for this problem are quite tricky, and it's not very straightforward how you would begin to do it also. So these are some of the points that I wanted to discuss in the roots of unity part. With this, we come to the end of the polynomial section, and basically that is the end of the course. There will be a lot of problem sets that will be shared uh, in each of the sections. We have 25 sections and more than 60 lectures, 45 hours of content. And if you go through the problem sets here, given in each section, you should be able to do really well in Olympiads, because I have tried to cover all possible concepts and different types of problems that you might encounter. So please do attempt the problem sets carefully. Go through the problems that were discussed in the videos again, and try and do them yourself. And if you have any problems, please do reach out to me and I will try and solve those doubts with you. So that's it for the course. Hope you learned a lot from it, and I'll see you next time.